Okay, here's a video about polarity where I'm just going to go through some examples of how to figure out if something is polar or nonpolar. And so this flow chart is very helpful. Of course, you wouldn't get it on the test, but you should kind of commit this to memory. So if something's bent or trigonal pyramidal for a geometry, that's always going to be polar. If it's not bent or trigonal pyramidal, so like if it's linear, trigonal planar, or tetrahedral, you have to look at this symmetry. And if it's symmetrical, it's nonpolar. And if it's not symmetrical, then it will be polar. So I'll be going through some different slides here to help you understand some examples anyway, so you can see what that's like here. So anyway, let's do a couple of examples. So let's say we had SO2. Okay, so the first thing would be to draw the Lewis structure. And so you would end up with something like this, S. It's going to be triple bond or double bonded to one oxygen, single bonded to another one. And so I'm not really taking the time to go through the Lewis structures. But you see that it has three domains, 1, 2, 3. That means it's bent. And because it's bent, you know then, hey, it's polar, because bents are always polar. All right? So that's the first one. Example, let's try another one here. Okay, let's see here. Make it switch slides here. Okay, so pH 3. So if we draw pH 3, so that's going to be, I got to go to the pen here. All right, so we go P, H, 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 and then there'll be a lone pair up here. And so if you count, that's 4 domains, and so that's going to be trigonal pyramidal. And because it's trigonal pyramidal, we know that it's polar. All right, let's try another problem. Okay, HCO2. So if you draw the Lewis structure for HCO2, I think I wrote that formula down wrong. I wanted the formula to be H2CO. So that's the wrong formula. So if I go H2, so we got a carbon, hydrogen I mean, and then a double bonded oxygen. And so we would have that right there would be the structure. And so you would look at that, there's 3 domains. And so that's going to be trigonal planar. So this structure is trigonal planar. Now, what you do is you look at it. If you look at the surrounding, like the carbon, are all 3 things surrounding it the same? Okay, and you would see that they're not the same. So it's not symmetrical. Therefore, this one is polar. Okay, let's try another one here. Okay, BF3. So you draw BF3. Now remember that boron is one of those that has an exception to the octet rule. It doesn't have a complete octet. It only has 6. So this is BF3. And so BF3 has 1, 2, 3 domains around it. That's trigonal planar. Okay? Now you're going to look at it and say, okay, are all 3 things the same around the boron? And they are the same. So it would be symmetrical. And so this is a case of one being nonpolar. So let's just review something from the last one. The last slide was this right here. It was like that. They're both trigonal planar, but this one, all 3 things are the same. It's symmetrical. It's nonpolar. This one, all 3 things were not the same, so it's not symmetrical, so it's polar. That's how you can tell trigonal planars apart, or tell whether they're polar or nonpolar. Okay, SiO2. So if you were to draw SiO2, silicon would go in the middle. It's going to be double bonded to oxygens like that, and then you'd have the lone pairs. And so you would have 2 domains, and so you would see that that's linear. So Si2 is linear. Then for linear ones, you're just looking and saying, okay, are the 2 things on the outside, are they the same? And if they are, then it's going to be symmetrical and it's going to be nonpolar. So this one is an example of a linear one that's nonpolar. You see the dipoles, this oxygen is going to pull that way on the electrons, and this oxygen is going to pull that way, but the forces will be equal and opposite, so they're going to cancel out. So that's why it's nonpolar. All right, here's O2. So you can draw O2, the Lewis structure for O2. Okay, O2 is linear, and if you look at it, it's going to be linear, it's going to be symmetrical because there's not one thing on one side different from something on another. So it's going to be nonpolar. Okay, CF4. So you draw CF4. So this one is going to be a carbon with 4 hydrogens around it, or 4 fluorines, not hydrogens. Okay, now what you'll notice is that it is tetrahedral, but all 4 things are the same. It's very symmetrical, therefore it's nonpolar. Okay, CH2F2. So C, H, H, F, F. Okay, that's tetrahedral. All right, but if you look, not all 4 things are the same. Because all 4 things are not the same as you go around this molecule, it's not symmetrical. And so therefore, it's going to be a polar molecule. Now with tetrahedrals, it's very simple to tell if they're polar or not. Let's look at the example on the previous page, and that was CH4. If all 4 things are the same, nonpolar. If all 4 things are not the same, polar. That's the easy way to tell it apart. Okay, I think that's going to be it for this video. Just need to, oh, I guess here's one more. HF. So if you draw HF, you would get that right there. That's a linear molecule. Okay, are the 2 things the same? No, therefore it's going to be polar. Okay, that's it for this video. But what you do need to know is you do need to remember that bent or trigonal pyramidals are always polar. But with linear, trigonal planar, or tetrahedrals, you have to look at the symmetry to figure out if they're polar or not. All right, that's it with this video.